I hope that I am audible to every student. Am I audible? Am I audible to every student? Am I audible to every student? Am I audible to every student? I would like to advise you to increase your volume of the system and increase the volume of the YouTube live. You increase the full volume of the YouTube live, you increase the full volume of your system. Otherwise, you are not able to hear me. Am I visible? Is my screen is visible? Am I audible now? Am I audible now to all the students? Voice is too low. You increase your volume. You increase your volume of your system. Visible quite clearly, but sir, you are not audible. Okay, now I am audible. Now I am audible. Am I audible now? Am I audible now to every student? Yes, sir, you are audible. Yes, sir, you are audible. You are now audible, sir. Now you are audible. You increase your volume of your system. You increase the full volume of your system. Make the volume of your system 100%. Makes the volume of the YouTube live 100%. Makes the volume of YouTube live 100%. Okay, so let's start. Today we are starting computer organization and architecture theory. And today we are explaining chapter number 2 from module number 1, which is known as computer instruction set. This is our lecture number 6 from this chapter. Today we are about to explain what is addressing mode. In the previous class we have explained what is instruction, what is instruction set, what do you mean by 0 address instruction, 1 address instruction, 2 address instruction, and we have also explained what is instruction cycle. We have observed an instruction cycle is a combination of opcode fetch, instruction decode or opcode decode, and operand fetch. Then we execute the instruction and write the result into the proper location. Now today we are concentrating on addressing modes. If we concentrate on addressing mode, we can able to observe that the ALU of the CPU executes the instructions as detected by the opcode field of the instructions. The instructions are executed on some data stored in register or memory. For example, say if we take example, say LDA 9050, this is an instruction. This instruction takes the data from 9050 memory location and transfer the data to register A. LD stands for load directly. Load directly to where? Accumulator. To accumulator from where? From 9050 memory location. So here we are observing it is taking the data from memory. And let's take another example, say add B. In this instruction we are receiving our first data from the accumulator, as because it is one address instruction, and we are receiving our second data from B register. So we are taking the data from register A and register B, and we are storing our result to register A itself. So that's why it is saying the instructions are executed on some data stored in registers or memory. So how the opcode field of the instruction describe based on that instruction operation performs. Look at that. The opcode field of this instruction is representing LDA instruction, and opcode field of this instruction is represent add instruction. So we perform the addition operation here, and as because it's a load instruction, we perform the load operation here. So the different ways in which the location of an operand is specified in an instruction are referred to as addressing mode. This is very important point to remember. For example, if you take this example, here my data on which I am operating is stored in a memory location 9050. So I can say my data is hiding, my original data is hiding inside a memory location 9050. In case of add B, we are observing that the data on which I am operating is hiding under A register and B register. So this is we are observing. Let's take another example. If we take another example, say CMA. CM stands for complement, and A for accumulator register. So what we do, this is accumulator register. So what we do basically in this example, in this instruction, look at that, there is no operand field or operator field, there is no operand field or operand location field such as memory or register, which will store the address of the operand or the operand itself. What this instruction is basically doing, we are basically complementing the value of the accumulator. So AC bar, we are performing AC bar here, and result is stored in AC. In this instruction there is no operand field operand field like operand location, memory location, register location. Operand data is not given directly, so these types of instruction is implicitly defined where the data is stored. This instruction is implicitly defined that accumulator is the register where the data is stored. So this is the one way or one approach for hiding your operand specified by the definition of your instruction. Let's take another example, say MBI A comma 55H. Let's take this example. In this example, 55H is the hexadecimal data. We are specifying this hexadecimal data directly inside the body of the instruction or inside the definition of the instruction. What we are doing, we are transmitting the 55 data to accumulator register. Okay, so here we are specifying the data immediately. That's why we are not hiding anything. We are immediately specifying on what data we are basically doing. So this is maybe another approach of defining addressing mode. A computer uses variety of addressing mode. More the addressing mode computer uses, more different kinds of instruction computer will use, and more different instruction will use by the computer, then computers instructions will increase in the instruction set. So what is the main advantage of using different types of addressing mode? Computer uses different types of addressing modes for the following purpose. First one is it will give programming versatility and flexibility to the programmer with respect to the number of instruction and execution time by providing various addressing mode. For example, execution time of LDA 9050 will be different from execution time of ADB. Execution time of CMA may be different from ADB, may be different from MBIA, 55. So there is a versatility in the execution in the time in the program. There is a versatility in the number of instruction present in the instruction set. Programmer may use lots of type of instruction rather to use a single instruction or at certain types of instruction. Next in point number 2 we are observing it will reduce the length of the instructions or the size of the program. Very simple. MBI A, 55 it is it is basically 2 byte instruction. LDA 9050 it is 3 byte instruction. Add B it is 1 byte instruction. CMA it is 1 byte instruction. Similarly, we are observing that CMA is a 0 address instruction. Add B it is basically a 1 address instruction, and MBI A, 55 it is 2 address instruction. So it will reduce the length of the instructions or size. We can vary the instruction length and size, etc. Instruction length and size, etc. Instruction size denotes how many bytes basically it will take, and instruction length basically denotes that how many, what this instruction is all about. Is it 0 address, 1 address, 2 address, 3 address? Because of these two parameters are associated with the capacity of memory. Okay, so that's why addressing modes gives us this variety. So programmer can write lots of types of instructions, and they can use these instructions for writing their program. So they can easily write their program. They do not face any problem. Okay, so let me take your questions now. Any question from slide 1? Any question from slide number 1? Do you have any question from slide number 1? If you have any question from slide number 1, then you please tell me. You please tell me if you have any question from slide number 1. I am not receiving any responses from your side. Student is saying no question, sir. How the size reduced? Can you please repeat? Very simple. Size will help us to reduce the instruction, basically reduce the size and length of the programs will reduce the basically program. For example, let me explain it. Suppose we, as I told you earlier, that x is equal to a plus b minus c plus d. If we want to express this expression, if we are using the 3 address instruction, then what happen? We can write this program with the help of 3 sentences. Our first sentence is add r1 comma a comma b. Next, our next sentence number 2 is add r2 comma c comma d. Our third sentence is store x comma r1 comma r2. So 3 sentences are required here, or 3 instructions are required here. So size of the program is basically contains 3 sentences or 3 instructions. But if we represent it by means of the 2 address instruction, first of all load C, then add 1 address instruction, then first of all load r1 comma say 2 address instruction r1 comma c, then add r1 comma b r1 comma d. Next, store t comma r1. Okay, next again load r2 comma a. Next, add the value of add a and b, that is r2 comma b. Then what we need to do, we need to subtract. So subtract r1 comma r2, result is stored in r1. Next is we need to store the result in t location, so t comma r1. So look at that, 1 2 3 4 5 6 7. We require 7 instruction here, and whereas we require 3 instruction here. More instructions means more space is required. Less instruction means less space is required. Okay, so this is how the addressing mode is basically helping us to reduce basically the size of the program, length of the instruction. Look at that. If we are using this instruction, then it is using 2 address instruction. If you are using this instruction, it is using 3 address instruction. If you are using LDA, the length is 3. If you are using if you are using LDA, then the length of this instruction is 3 bytes. And if you are using the CMA, length of this instruction is 1 byte. If you are using MBI, then length of the instruction is 2 byte. Next, our first types of addressing mode is implied addressing mode. In this addressing mode, the operand or data, this is important, operand or data are indicated implicitly by the instruction. Look at that, as I told you earlier. For example, CMA. CM stands for complement, A for accumulator. What do you mean by that? That means the value of the accumulator is once complemented and the result is stored in the accumulator itself. Is any operand is there? Is any operand is specified in the definition of the instruction? No. Is any operand location is specified? Operand location means such as register is specified to or memory is specified to represent the operand? No. So there is no operand or operand location such as register or memory. So it's a zero address instruction. It implicitly says all the operation will done with the accumulator. Hence, it is in implied addressing mode. Next is RAL. RAL stands for RAL. RAL stands for rotate accumulator left with carry. So what happens is that we have a data stored in accumulator 1, 2, 3, 4, 5, 6, 7, 8. So 0, 1, 2, 3, 4, 5, 6, 7. So 1, 0, 1, 0, 1, 0, 1, 0. We need to rotate this data. Suppose the value of the carry flag is 0 initially. So what happens this? First of all, we need to rotate this by 1 bit towards left. First of all, this 1 bit will take the position of the carry. Now this is empty. Now 0 bit will take its position. Next 1 bit will take this position. Next 0 bit will take the position. Next 1 bit will take the position. Next 0 bit will take the position. Next 1 bit will take the position. Next 0 bit will take the position. Now this bit is empty. Now the value of the carry flag will comes here. That means this becomes 1. So this is RAL. In the RAL instruction, we are not observing any operand field, and we are not observing any operand location such as register or memory. So that means it is that this is the definition of the instruction, and in the definition of the instruction we are observing there is no operand field, operand location field. That's why we can imagine that all the operation will done in accumulator. So as CMA, look at that, all the operations is done with accumulator. Here also all the operations is done in accumulator. So this is in implied. We have to use accumulator that is not specified in the instruction, that is implicitly specified. User or programmer or computer will automatically understand when CMA is written, when RAL is written. Next, our next addressing mode is immediate addressing mode. Very simple. MVI A, 06. So 06 is the data. We need to transfer the data 06 immediately to a or accumulator. MV stands for move. MV stands for move. So we need to move the data from where? From which data? The data is 06, so it is my source. Next, to 06 to be moved where? In the accumulator, so it is my destination. So what is the micro instruction written for this instruction? Micro instruction is we need to move our data to accumulator, and what is our data? Our data is 06. So this is our instruction definition, MVI A, 06. This is our instruction definition. How many address field is there? 1 and 2. This is destination, this is source. Is source is directly specified or immediately specified? Yes. That's why it is in immediate addressing mode. I stands for immediate. I stands for immediate. Similarly, ADI 05. ADI 05 means we are adding the data 05 with the content of accumulator, and result will be stored in the accumulator. So 05 data which is to be added with the accumulator is immediately specified. That's why it is immediate addressing mode. I means immediate. AD means add. So we are performing the summation operation or addition operation here. So in this mode, the operand is mentioned explicitly in the instruction. Look at that. 06 is the operand. It is explicitly mentioned. 05 is the operand. It is explicitly mentioned. Okay. In other words, an immediate mode instruction contains an operand value rather than an address of it in the address field. So look at that. There are two address field or two operand field here. One is represented by A, another is represented by 06. Look at that. There is only one address field is there, and that is being replaced by the data or the operand, that is 05 here. So this is directly specified. This is immediately specified. So that is why it is in immediate addressing mode. Third addressing mode is stack addressing mode. I have already explained what is stack addressing mode. In stack organized computer, we use stack address instruction. Stack address instructions are, say, push B. Next is pop D. Next is add. What do you mean by add? Then what happens? The top two element of the stack will be popped. Okay. Suppose push B, then push A. Then what happened? The value of the accumulator, which is say 03, will be pushed into the stack. Next, push B. That means the value of the B register, let's say value of the B register is 02. It is pushed into the stack. Next, pop. Say. Next, suppose I am writing, suppose add. What do you mean by that? That means automatically first data will be popped. Our first or topmost data is 02, which is the value of B. Next, second data will be popped. Our second data is the data of accumulator, which is 03. It is popped. Then these two will be added. 02 plus 03, that is 05. These two are added. And this result 05 is stored in the stack. Okay. Similarly, whenever we write pop D, then the value of the D register, then the value of the stack will be popped and stored in the D register. Okay. So in stack based computer, we use these types of stack address instruction. In this addressing mode, all the operands for an instructions are taken from the top of the stack. Look at that. 02 is popped up from the stack. 03 is popped from the stack. The instruction does not have any operand field. Look at that. Sub, this does not have any operand field. Add, it does not have any operand field. So it's a zero address instruction. So it only uses the opcode of add. It only uses the opcode of sub. What happens in case of the sub? What happens? Suppose inside my stack I have two data. One is 03, another is 05. So we pop first of all 05, then we pop 03. Whenever I write sub instruction, automatically these two will be subtracted. The value is 02. As because it is pop, they are not there. So 02 data will be now pushed into the stack. So 02 is the difference of the subtraction. We need to understand that. So this is a zero address instruction. This sub is basically a zero address instruction here. It does not have any address field. So both the operands are the topmost two L positions of the stack. Look at that. 05 is the topmost position and 03 is the top -1 position. Topmost two positions will be popped. Then we perform the operations. And topmost positions and topmost -1 position, topmost plus -1 position, they are, all of them are basically are in consecutive locations. If it is stored in 8 FFE, it is stored in 8 FFF locations. These are basically hexadecimal addresses. Okay, so when sub instruction is executed, two operands are popped out automatically from the stack one by one. So look at that. First of all, 5 is popped out. Next, 03 is popped out. Okay, then what happened? Then we perform the operation, then we generate the result, and the result is pushed onto the stack. So look at that, our result is 02. We push the result into the stack. Okay, so there is no address field used. Look at that subtraction instruction we are using. No address field is used, no operand is used, no operand location is used, neither register nor memory. Okay, so this instruction is very short way to represent these types of instruction. Only if we specify the opcode of sub, then this instruction can be easily understood by the machine or computer. Okay, we do not need any other thing. Next, register direct addressing mode. In this mode, processor register holds the operand. For example, say add R1 comma R2. So look at that, R1 is holding an operand, say 03, and R2 is holding another operand, say 02. So the register, processor register, R1 is a processor register, R2 is a processor register. R1 is holding an operand 03, R2 is holding an operand 02. In other words, the address field of the address field is now register field. Look at that. Add R1 comma R2. So there is a first address field is basically specified by register R1. Our second address field is specified by register R2. So now these two fields are register field which contains the operand required for the instruction. So R1 is basically holding 03, which is our operand for first source operand. R2 is holding 02, which is our second source operand. We need 03 and 02 for addition operation because it's a binary operation. What happens whenever we run this instruction add R1 comma R2? Whenever we run our instruction add R1 comma R2, the value of R1 and the value of R2 will be added and the result will be stored inside the accumulator. Okay, inside the register R1. Very sorry, this will store inside the register R1. This is our first source operand, this is our second source operand, and this is our result is stored. So our first source operand is 03, second source operand is 02, 03 plus 02 is 05, which is stored in R1. So look at that, our first source operand is stored inside R1, which is a register, which is specified in the instruction. So if we go directly to the register R1, we can able to get the data. So next we are specifying 02 data inside R2. What is R2? It is a register. Is it specified directly in the instruction? Yes. So if you go directly into R2, we can find the data 02. So it is also a register field. So this is basically in register direct addressing mode. Okay, so this is basically the register direct addressing mode. So out of 2 to the power k registers in CPU, one register is selected using k number of bits naturally. So suppose we have an 8-bit data. So how many data we can able to access? 2 to the power 8. Suppose we have a 16-bit address. So how many addresses maximum we can access? 2 to the power 16. As simple as that. Similarly, if one register is accessed by k bit, how many registers we can access? 2 to the power k number of registers we can access. This mode is useful to a long program in storing the immediate result in the register rather than from the memory. Okay, so we are observing that the value of R1 and value of R2 is immediately storing inside a register, not into a memory. So in these cases, we require these types of instruction whenever we need to execute the instruction in a very short way, in a very precise way, where we do not need to access any memory. Because if we want to access a memory, that means memory read or write operation, if we want to perform, it will take lots of time. So this will result in fast execution. Since the register addressing is much faster than memory addressing, we are using this. Next, our fifth is register indirect addressing mode. So what is happening in register indirect addressing mode? Suppose suppose LDAX B. So our opcode is representing LDAX. What LDAX means? LD stands for load, A for accumulator register, and X for indirect. We are storing our address, we are storing a memory address in BC register pair. So this is our BC register pair. So we are storing an address in BC register pair. Say this is B register, this is C register. B register is holding suppose 90, C register is holding suppose 50. Then what happened? This is 9050 location, and inside it we have a data say 07. So what we do, LDXB means we directly, first of all, we need to understand that which register is specified here. Which register is specified? There is a register pair specified by means of indicating B, that is BC register pair. What is the value of B? 90. What is the value of C? 50. What is the total value of BC register pair? 9050. Is it a data? No. Is it an opcode? No. Is it an address? Yes. Then go to 9050 address. What is the data? 07. Then transfer this 07 data to the accumulator. So this is what happens in case of the register indirect addressing mode. In register indirect addressing mode, the instruction specified an address of the CPU register that holds the address of the operand. Look at that. Here in the instruction definition, BC register or BC register pair is specifying the address of a memory location 9050, which is storing the original data 07. Now we are transmitting this 07 to accumulator register by means of the opcode, that is LDAX. LD stands for load, A for accumulator, X for indirect. Okay. So I would like to hear it from you if you have any question. Do you have any question? Let me see your questions first. Do you have any kind of questions? Immediate repeat. I don't understand the question. That means you are asking to repeat immediate addressing mode. So in immediate addressing mode, you are observing that we are immediately specifying the data 06 or 05 inside the definition of the instructions. Next question. Sir, how the size reduce can repeat? Already answered this question. Sir, you are not audible properly. I think I am now audible. Sir, you are not audible properly. I think now I am audible. Am I audible to everyone? Am I audible to everyone? Sir, will you get the PPT? Will we get the PPT? Some of us are having a bit internet problem. Okay, next class, actually I need to talk to my HOD for circulating the PPT. After consulting with my HOD, I can circulate it. Next is, sir, what is 07 in the memories? What is 07 in the memory? What is 07 in the memory? 07 is the data present in the memory. In register indirect addressing mode, 07 is the data present in the memory. Next question. Sir, can you help us with PPT for our convenience while studying? Obviously, I need to consult with my HOD, then I will circulate the PPT. So, there is no other doubts, so we can proceed further. So after register indirect addressing mode, our next addressing mode is auto increment and auto decrement addressing mode. So what happens in auto increment addressing mode is, it is similar to the register indirect addressing mode, except after or before register content is used to access the memory, it is incremented or decremented. Okay, so it is necessary to increment or decrement the register. So after every access to an array or data in memory. So if the address stored in register refers to an array, so this can be easily achieved by this mode. Suppose we are accessing basically an array 1, 2, 3. So this is the starting address, say 8000. This is 8002, 8004, 8006. Data stored there is 02, 04, 06, 08. Now what we are doing, we are writing the instruction, say INXH. So in INXH, what happens is that this is our opcode and this is representing HL register pair. So what we do, we directly go to the HL register pair. The value of H is initially suppose 8000, so 8000. Whenever I perform INXH, what happens? The value of H will automatically incremented by the offset. What is the offset value? Offset value is the difference from the current position to the previous position. Current position address is 8002, previous position address is 8000. What is the difference? 02, so 02 is the offset. So HL register pair value will be incremented by offset. What is the offset here? 02. So we added, so 80 is now the value of H and 02 will be the value of L. That means now we are pointing Now we are pointing to the location or to the data 04. Now we are basically pointing to the data. So what we are basically doing, the HL register is pointing and memory address which is present here in this array and the data presented. Whenever I perform auto increment addressing mode, the value of the HL is automatically incremented by its offset. Now previously it is pointing 8000. Now it is pointing 8002. We are basically now pointing 8002's data. Similarly, auto decrement addressing mode, say DCXH. Similarly, suppose we are pointing 8006. So after DCX, DC for decrement, X for indirect. So this is in indirect addressing mode. What happened in this case? The value of the H and L register pair is 08 and 06. It will be decremented by the offset. What is the offset value here? Current position plus previous position 8004, current position 8006, difference is 02. So 02 is the offset. If we subtract, then we can able to get the value 8004. So this is now the current value of HL register pair. That means HL register pair is pointing 06 data which is stored inside 8004. So DCXH is in auto decrement addressing mode, INXH is in auto increment addressing mode. Next, direct memory addressing mode or direct addressing mode. For example, STA. For example, say LDA. So LDA, say 2500H. It is an hexadecimal address. So LDA is specified in the opcode field of the instruction format, and 2500 is specified in the address field or operand field or operand location field of the instruction format. It is a memory address. We go to 2500 memory address. What is the data here? Say 07H is the data here. What we do? We load this data because LD stands for load, A for accumulator. We load or transfer this data to the accumulator. Similarly, if I write STA, say 2500H, then what happens? ST for store, A for accumulator. That means we are going to store the value of the accumulator to 2500. 2500 is specified in the address field, which is memory. So we directly go to the memory address, okay, and the value of the accumulator will be transmitted over there, okay. So this is happening here. So my point is that 2500 is basically a memory address. We are transmitting our data from accumulator to this memory address directly. So if you go to the direct memory address, we can able to read the data or we can able to write the data. I repeat, the memory address where data needs to be read or where from or to where the data needs to be written, it is directly specified in the instruction definition. That's why they are in direct addressing mode. Okay, after memory direct addressing mode, we have a memory indirect addressing mode. Okay, memory indirect addressing mode. For example, say MOV A, M. So MOV is basically my opcode here, and A and M are by basically the operand locations. So it indicates that M is my source operand location, A is my destination operand location. So what I need to do, I need to transfer the value of the source location to destination location, that is accumulator. What M basically denotes? M basically denotes the value of the HL register pair. What is the value of the HL register pair? It is basically a memory address, say 8000. Now we go to this memory address 8000. We found the data, say 07 is the data present here, and we transfer this data to accumulator register. So in memory direct indirect addressing mode, the memory address is not directly specified in the definition of the instruction. Rather, it is indirectly specified. You look at that, here the memory address is indirectly specified by a capital M variable, and capital M variable denotes the HL register pair, and HL register pair holds the original memory address. If we go to the original memory address, we will find the data. Okay, so as move R1 comma X, so same is here. The X is basically a register or maybe some other locations, okay, other memory address where the original address of the data is stored. This is the 8007 is my original data. 07 is my original data, and 8000 is my original address. Our original address is known as effective address. Our original address is known as effective address. Okay, so we can also calculate effective address by address part of the instruction and content of the CPU of a CPU special register. Let's see what are the CPU register. For example, say relative addressing mode. What happens in this case? In relative addressing mode, the effective address is obtained by adding the content of the program counter PC register with the address part of the instruction. Look at that, address part of the instruction is 20, which is basically my offset. Suppose my program counter value is 2000, and then 2000 is my program counter value, and my offset value is 20 here. We add this two, so what is the address? 2020 is the offset here. So what happens is that means it indicates that 2020 is the next address where I need to jump. JR stands for jump. It is basically a kind of branch location. So this is basically saying that it is adding the content of the program counter. What is the value of the program counter here? 2000. With the address part of the instruction. What is the address part or offset part of the instruction? 20. What is the new address? 2020. Where we need to jump? At 2020. We need to jump at 2020. Okay, so we understand that. Okay, these types of instruction is mostly used in case of basically the loop, in case of subroutine call or function call, in case of returning from the function. These types of relative addressing mode is used. So the instruction specified the memory address or of operand. The instruction specified the memory address of operand as a relative position of the current instruction address. Okay, so this is the relative position of the current instruction address. This is the relative position. 20 is the offset, which is basically the relative positions, and the branch location is computed by adding the offset value 20 with the current value of the program counter. So the instruction JR20 basically requires 2 bytes, for one for opcode of JR and another for offset value 20. So consider the instructions stored in the memory shown in this figure. So if we concentrate on that, so 2001 is basically stored the offset required for this instruction, that is JR20 instruction. Offset is 20 stored here, and JR is the instruction, the opcode of that is stored in 2000. So what happens is that we retrieve the offset. What is the, so first of all we calculate what is the program counter value. Program counter value is basically, program counter will indicate the next instruction that is going going to be executed. 2000, 2001, next instruction is 2002. So we need to execute, we need to point 2002 instruction. So we need to point 2002 instruction. So now 2002 and 20 will be added. Result is 2002 plus 20, that is 2022. We go to 2022, we jump to 2022 address. So in this way we are basically calculating the operations in PC relative addressing mode. Next is index addressing mode. In case of the index addressing mode, effective address is determined by adding the content of the index register or XR. Okay. Okay. So suppose with the address part of the instruction, this mode is useful in accessing an operand array. Suppose we have an array, say the base address of the array is 8000, next is 8002, this data is 04, this data is suppose 06, in this way 08, 10 in this way. So 04, 06 in this way. What is the base address? 8000. So 8000 will be stored in the index register. Now suppose index register, suppose the instruction is LDA suppose the instruction is LDA say adding the content of the index register with the address part of the instruction. So offset part should be defined inside the instruction. So what is the offset? The difference between the current address and difference between the next address, that is the offset, which is 02 here. So LDA 02 if I write, we automatically understand that 02 is the offset. So we are basically adding the offset and the value of the index register. So what is the value here that we have generated? 8000 plus 02, that is 8002. So we go to 8002, what is the value? 06. We load this value 06 to our accumulator. So that is how the operations is being performed in the index address mode. Next, base register addressing mode. In this addressing mode, the same way happening. The content of the base register will be added with the offset which is specified in the instruction. So whenever we need to relocate our programs in the memory, we use this addressing mode. What is relocation? Relocation is a technique of moving the program or data segment from one part of the memory to another part of the memory. Relocation is an important feature in multi-programming system. In this mode, the current content of the base register, say the base register value is 1000 and the offset value is 02. What we do, we add these two. What is the ultimate address? 1002. So we go to 1002, suppose there is a data 07, we fetch this data and transport it to accumulator. Okay. Or maybe from accumulator the data is transported to the 1002. So in this mode is similar to index addressing mode, but what is the difference? Exception is one way that they are used. In index addressing mode is used in case of accessing array, but base register addressing mode is used for relocating a program in memory. Okay, a base register holds the starting address of a memory array or operands, and the address part of the instruction gives the displacement value or the offset value related to the starting address. The base register addressing mode has an advantage over index addressing mode with respect to the size of the instruction, because the size of the instruction in first case, that means in base register addressing mode, is smaller than the index register addressing mode. Next is instruction set. We are observing that instruction set of a processor is a collection of all the instructions present in it. Instruction set has the following characteristics: completeness, efficiency, regularity, compatibility. Okay, completeness means all the instruction, it has to be capable of completing all the operations. Next, it has to be efficient, it has to be regular, it has to be compatible. Next, there are lots of instruction type: data transfer, arithmetic, logical, program, control, etc. And these are data transfer related instructions such as move, load, store, exchange. Arithmetic instruction: add, c, sub, multi, div, etc. Logical: and, or, or, not, shift, rotate, convert. Program controller: jump, c, rate, net, int, test, etc. And input output controller: in, out, start IO, halt IO, test IO, etc. So we are ending our lecture here. Next class it will be continuing with the further discussion.